Okay, this video I want to see how regression with dummy variables connects to some of the things we did earlier in the term. And there are also a few loose ends to tie up before we finish. First, I want to go back and look at some problems that we've already seen in earlier chapters. The first one is number 14 in chapter 13. You might remember this as a two-sample t-test homework problem. We are going to compare the mean amount spent on holiday by golfers versus skiers. And the complete data set is shown here. We can turn this into a regression problem by realizing that our y variable is the amount of money spent and our x variable is type of holiday. In this example, there are two possible types of holiday, golf and skiing. So we need one indicator variable to define it. I'm going to make an indicator for skiing. And the data set could be set up for regression like this. Now let's compare the two computer outputs. First, here is the two-sample t-test output from Excel. There are a few things I want to point out here before I show the regression. First, the two sample averages are shown here. And the difference between them is the foundation for the t-statistic seen here with 13 degrees of freedom and this p-value. This is not significant, so we cannot say that there is a difference between spending between skiing and golf holidays. Now let's look at the regression with the indicator variable. It's a little hard to find the common ground at first, but it is there. The most obvious connection is the t-test for the indicator variable. It is exactly the same as the other output. And it also comes with the exact same degrees of freedom and p-value. But there is important information in the regression coefficients as well. The indicator variable can only equal 0 or 1, and it equals 0 for golf holidays. Therefore, the expected money spent on golf holidays is the intercept. And this is exactly the same as the sample mean for golf holidays. When the indicator variable switches from 0 to 1, then this slope coefficient is added to the intercept. So this slope represents the difference between skiing and golf holidays. And this is exactly the difference between the two sample means shown here. So interpreting the regression output is actually very similar to the two-sample t-test. I would begin with the intercept and interpret this as the mean amount spent on golf holidays. Then I would look at this slope coefficient to see that skiing holidays are, on average, about $720 more expensive. Then, looking to the side, I would see that this difference is not significant and conclude that skiing holidays are no more expensive than golf. Before moving on, I want to point out a couple of other connections. The pooled variance is exactly the same as the MSE. If you look carefully at the two calculations, you'll see that they are equivalent. Also, then the standard error of the slope is the denominator of the two-sample t-test. Next, let's move on to a one-way ANOVA problem. This is number 4 from chapter 14. We have 3 samples, one for each type of job. When we turn this into a regression, our x variable would be type of job. Since there are 3 possible categories for job, we need 2 indicator variables to fully define it. I'm going to make indicators for finance and management. And the data set will look like this after we've prepared it for regression. And I want to point out the category that is represented by all zeros. In this example, that category is marketing. I like to call this category the baseline because, as we will see, everything else is compared back to the baseline. Let's look at the computer outputs, beginning with the one-way ANOVA table. Take note of the 3 sample averages, and then the p-value is significant at 5% level, so we can conclude that the mean values for the 3 types of job are not all the same. Next, let's look at the regression output. First of all, the entire ANOVA tables are exactly the same for both. Now let's focus on the regression coefficients. If all the indicator variables are equal to 0, then the regression equation is just the intercept. This represents the expected value for the baseline category of marketing. And we can see that this is equal to the sample mean for marketing. Then the slope coefficients represent the difference between that category and the baseline. So the -1 value for the slope of finance means the mean value of finance is 1 less than marketing. And the +2.5 value for management means that the mean value for management is 2.5 greater than marketing. We can see the same relationships in the sample averages in the ANOVA output. Next, let's look at the standard errors and t-tests for the slope coefficients. These are exactly the same as the Fisher LSD t-tests that we saw in the multiple comparisons video. And in that video, I explained how this has problems with type 1 error rate, so we prefer the Bonferroni adjustment or Tukey's method, but the Fisher LSD gives us a good place to start. And we can see here that neither of these differences is significant at 5% level. And this may seem like a contradiction, since the F-test in the ANOVA table says that something is different. But notice that the regression output doesn't have all possible differences. It only has the differences involving the baseline. So this output does not have the difference between finance and management, and that must be the one that is significant. Next, let's look at a two-way ANOVA example from the interaction video. This data is about salaries, and there are 2 factors, or X variables, occupation and gender. With a total sample size of 30, you can see the complete data set here. And let me just remind you about this data set. Here are the factor level combination means. And this is the graph, clearly showing the interaction. Let's prepare the data for regression by creating indicator variables. Occupation has 3 possible categories, so we'll need 2 indicator variables for it. And gender has 2 possible categories, so we'll need 1 indicator variable for it. And just to give you another way of thinking about it, I'm going to begin by thinking about my baseline categories. For this example, I'm going to choose male pharmacists as my baseline. So they'll be the observations where all the indicators will be 0. Therefore, I need indicator variables for all the other categories: financial manager, computer programmer, and female. The data sets are shown side by side so you can see how they are coded for the indicator variables. And notice how the baseline male pharmacists are all 0s. Next, since we also want to study interactions, let's add the interaction variables. We have the interaction between financial manager and female, and the interaction between computer programmer and female. Now we're ready to do the regression and compare the output. Let's begin with the two-way ANOVA output. We can see that at 5% level, there is a significant interaction between occupation and gender. And back in that video, I cautioned you that when you see a significant interaction, then it becomes very difficult to distinguish row and column differences from interactions, so we tend to just ignore the rest of this. Ignore these F-test results and just leave it by saying that there's an interaction. Anyway, let's look at the regression outputs, and let's begin by looking at the ANOVA tables. The error and total rows are exactly the same for both. And the regression row represents the full model with column, row, and interaction variables. So it is these 3 rows of the ANOVA, of the two-way ANOVA table, all rolled together into one. Let's look at the regression coefficients. Once again, the intercept represents the baseline, or male pharmacists. And ordinarily, the slope coefficients would represent the difference between that category and the baseline. So this -68 would indicate that financial managers make, on average, 68 less than pharmacists, and this -116 would indicate that women make, on average, 116 less than men. But we cannot just make statements like this, since these variables are all tangled together through interaction variables. We'll talk more about that in a minute. But before I do, I want to point out that the two-way ANOVA table showed a significant interaction between occupation and gender. Therefore, we'd better see at least one of the interaction variables be significant in the regression. And the interaction between financial manager and female is. I also want to point out that we could take this model and do some backward selection to it, beginning with removing the interaction between computer programmer and female. But I want to leave it like it is, since the full model has some interesting properties. Now let's look more closely at the regression coefficients from the model. We'll begin with the baseline group, male pharmacists. Since they have all zeros. And of course, if the indicators are all zero, then the interactions will be zero as well. And the intercept, 1047, is the expected salary for male pharmacists. If we let the female indicator variable equal 1, then we'll be talking about female pharmacists. But since the other variables are 0, then the interactions are also going to be 0. Then this gives us the expected salary of female pharmacists. Next, let's have computer programmer indicator equal to 1. If the other variables are 0, then we still get zeros for the interaction variables. And then this gives us the expected salary of male computer programmers. Next, let's switch on the indicator variable for financial manager. The interaction variables are still 0, and this gives us the expected salary of male financial managers. Next, let's look at female computer programmers. They have 1s for these two indicator variables. So we finally get a non-zero interaction, specifically the interaction between computer programmer and female. Then this gives us the expected salary for female computer programmers. Finally, we have female financial managers. They have 1s for these two indicator variables. So this interaction is also 1. And this gives us the expected salaries for female financial managers. It is worth noting that these expected salaries are all exactly the same as the factor level combination means that I showed you a few slides ago. And this always happens when we have a full regression model with all possible interaction variables. And finally, I want to remind you about the interpretation of interaction. Back in that video, I defined interaction as a special effect that applies to only one specific combination of categories, or one box of this table. And this is exactly what the regression interaction variables are doing. For example, the interaction variable between financial manager and female can only equal 1 if both of the indicator variables are equal to 1. And that would mean that we are here at the combination or intersection of financial manager and female. Since the interaction variable now equals 1, we have this additional term in the expected value. This term can only exist at this particular combination of categories, so it is just like a special effect just for this box. Next, I want to take the same data set and prepare it by starting with a different baseline. This time, I'm going to choose female financial managers as the baseline. Therefore, we need indicators for computer programmer, pharmacist, and male. And these would be the interaction variables that get us all the way to the full model. Let's look at the regression output for this model. First, I want to point out that the ANOVA table is exactly the same as before. So it doesn't really matter which categories you choose to make into indicator variables. As long as you have a full model, then they will effectively be the same. Next, I want to focus on the regression coefficients. These are all quite different from before, but they will lead to the same overall expected values. The intercept 635 now represents the expected salary for female financial managers, our new baseline. And if you work through the numbers like I did a minute ago, then you can find the expected salary for all 6 kinds of people. This is an exercise that I'll leave for you to do on your own because you already know the answers. You should get the same results that we had in the previous model. Okay, now I get a chance to mention some other topics that have in the past been included in this course. Even though we won't have a chance to learn how they work, you are responsible for at least being aware of them. You need to know their names and when it would be necessary to use them. I'm thinking directly of the question on your exam where there are 4 situations and you need to figure out the correct statistical test. Let's look at the first one, logistic regression. This is regression where the y variable is an indicator variable, so just ones and zeros. You have to use a completely different method called maximum likelihood, but you can develop a regression equation for the odds ratio of it happening. Basically, we can analyze something that either does or does not happen and study how the probability changes based on the x variables. So imagine a doctor studying the factors that affect the probability of having a heart attack, or a bank officer doing research on the probability of a small business defaulting on a loan. Several groups originally had ideas like this for their projects, so the usefulness of this topic should be pretty clear. Next, I want to do a very quick overview of what we skipped in Chapter 19. This chapter is devoted to what are called non-parametric statistics. And as the name suggests, none of these techniques involve parameters. So there aren't any population means or variances or any other parameter that we have seen so far. The main benefit of doing this is that we don't have to worry about assumptions in the background. Everything that we did this term had some assumptions. Even the good old 2-sample t-test assumes that the data is independent and normally distributed. The tests in Chapter 19 don't need any assumptions, and for this reason people call them robust statistics. The null hypothesis is also quite different when we don't have parameters. If we were doing something like a 2-sample t-test, then we couldn't talk about their means. Instead, we would say something like the distributions are identical versus not identical. As I said, there are several non-parametric equivalents to things that we already know, and these are the names that you need to know. The non-parametric version of the 2-sample t-test is called the Wilcoxon rank sum test. The non-parametric version of the matched pairs is called the sign test. The non-parametric version of block of one-way ANOVA is called the Kruskal-Wallis test. The non-parametric version of block design ANOVA is the Friedman test. And there is a non-parametric version of correlation called Spearman rank correlation. Next, I want to quickly explain why and when they are useful. And there are two situations when these types of tests are needed. First, as I already mentioned, these methods don't rely on assumptions. So we can use these tests when our data violates the assumptions of the test that we want to do in the first place. So suppose we have a data set that we want to do one-way ANOVA with. Well, after taking a closer look, we see that the data is very non-normal, or perhaps the variances are very different from each other. Remember that constant variance was one of the assumptions of ANOVA. If we can't trust the ANOVA F test because the assumptions are violated, then we can use the Kruskal-Wallis test instead. The second situation when these tests are useful is when dealing with ordinal data. This is categorical data, but with the added twist that they can be ranked in order. For example, the sizes small, medium, and large are categories, but they also have a natural ranking. So they are ordinal data. Or when you rate a restaurant on a scale of very bad to excellent, this is also ordinal data. This type of data doesn't fit in with the things we've done before. They are more than just categories, but not on the same level as quantitative numbers. These tests are the only way to adequately deal with them. And the tests in this chapter all start the same way. We would begin by ranking all of the observations from lowest to highest, and ties are allowed. So the actual numbers don't really matter, just the relative ranking. And then you have to do various calculations and compare them with tables in the back of the book, and it's all pretty tedious work, but that's basically how they are done. Finally, here is the data set for the questions at the end. This is a two-way ANOVA data set about GMAT exam scores. The two factors that may affect it are the student's major and type of review class. The complete data set is shown here. And then I converted this data into indicator variables to be used with regression. You can see that I used a baseline of arts and sciences and 3-hour review. So I have indicator variables for business, engineering, 1 day, and 10 week, and all the interactions as well. This is not the complete data set, but it's enough to see what I was doing. And here is the regression output for this model. And this is what you'll need to answer the questions coming up. So good luck with that, and I'll see you in class.